Welcome to the first topic of Module 5, Glass Examinations. We will begin by defining glass and discussing the common types of glass that are seen in a forensic laboratory. We will discuss the manufacturing processes used to make glass and then how glass breaks and the various characteristics that can be used to determine impact points and from which side the force was applied. We will finally discuss the common methods of analysis that are used on glass examinations in forensic laboratories. If we begin by defining glass, glass is going to be a solid that has been produced from a molten state without crystallizing. So glass can be considered a supercooled liquid. Glass is composed of several different chemical components, which are formers, fluxers, and stabilizers. But then, depending on the manufacturer's desired final end product, different additives can also be put into the glass composition to give it its color or to give it specific properties. There are several types of glass that are commonly seen in a forensic laboratory. Flat glass, which might be anything from doors, windows, mirrors, to molded glass, which might be something such as plates, glasses, jars, or bottles. Heat-resistant glass, which might be bakeware, some of the glass in the various light bulbs or sealed beam light bulbs, and also specialty glass that's going to have a special property imparted in that glass itself. So a lot of times it might be magnifying glasses or glasses that have special refractive properties, also stained glass. Glass is produced primarily from two different methods, either the float glass method or being molded. In the float glass method, the glass components are melted in a large furnace to create a pool of molten glass. This molten glass is then relayed to a float chamber, and in that float chamber, the thickness and the width of the glass is going to be controlled. As the molten glass continues down the manufacturing line, it's then going to reach an area where it is annealed, which actually hardens the glass, and then it will come out and actually be cut into the desired shapes for the glass itself. When glass is molded, it's initially also in a large furnace, creating the liquid glass, which will then be put into the mold, which is then annealed to harden the glass. So in both of the manufacturing processes, whether it's the float glass method or the mold method, we've talked about annealing. This is actually a controlled heating and controlled cooling at the end of the production of the glass that's going to help reduce the strain within. Some glasses may also go through additional processes,
and two examples of this are going to be either your tempered glass or laminated glass.
Tempered glass is going to go through an additional heating and cooling after the annealing stage. So it's going to be heated again to a softening point. It's not going to be completely liquid. It'll just be softened. So it's only going to go to about 700 degrees centigrade, but then it's going to be quickly cooled. This actually imparts a particular strain to the glass so that when it does break or shatter, it's going to be in very small pebble-like pieces that aren't going to have any sharp edges. This glass is used for safety glass in sliding glass doors, shower doors, and a lot of the various windows in vehicles. Another specialty glass is laminated glass, and this is actually two sheets of glass with a piece of plastic in the middle of the glass. That plastic may be clear, or at times it might have a little bit of color tint to it, like what is commonly seen in the windshield of vehicles. Once glass is produced, it is a supercooled liquid. So when it is initially struck with an item, it's going to start to bend before it's going to actually start breaking. But at some point, it's going to bend or stretch just a little too much, causing it to break. And what is initially going to occur are radial fractures. The top of this slide shows radial fractures radiating outward from that impact point. As these occur, they're forming small little ridge patterns on the edge of the glass itself. And you can see if you tilt one of the pieces of glass on its side, you can see these little ridges that are called Wallner lines, or at times also referred to as rib marks. These Wallner lines or rib marks are formed while that glass is actually fracturing. And they're also going to continue to form as that glass continues to break. As it continues to break, there's also going to be concentric fractures that are formed. And these concentric fractures are going to form in more of a circular pattern around that point of impact. So on this example, it's going to be the black lines that are going to be your concentric fractures, and the red lines are once again the radial fractures. We can examine the rib markings on the various fractures to help determine which side the force was applied to in some instances. This might be important in the case of a burglary where you're trying to determine, was entry made from outside or was it an inside job and the glass was just broken out to make you think that it actually was an outside job. So we can collect all of the glass from that area and then use the rib markings to actually determine which side the force was applied from. We can do this by applying the 4R rule, which is that ridges are formed on radial fractures at right angles to the rear. So you can see from this example, if we're looking at a radial fracture, the direction of force would have come from the left-hand side. It is very important if you're using the 4R rule to make sure that you're looking at a radial fracture. So it may be necessary to put enough of the window back together to see your impact point to know that you're actually looking at a radial fracture. Another characteristic that occurs when glass is broken is shown with a high velocity impact. And this is going to create a coning or a catering effect right by that impact area. A wider hole is going to be created on the exit side than where the force was applied from. So you can see in this example where a bullet, which would be very high velocity, is hitting the glass, it's going to initially start to bend, and then when it breaks, that exit hole is going to be a lot larger than the entrance hole. So if you have an impact area where you can actually examine that hole, if there's more glass missing on one side than the other, you know that that would be the exit area, instead of the entrance. You can also determine at times which impact occurred first. So if there are more than one impact areas, you can determine the order. In this instance, you can see that the impact that is on the very left-hand side of the slide, the radial fractures stop when they meet the fracture lines from the two previous impacts. So if you look at an actual piece of glass, you can sometimes determine from examining where the fractures meet each other which impact is first and which one is second. We can also learn several other things from glass itself depending on the size of the glass sample. If you're initially working with large pieces of glass, it might be that you can determine the direction of force or the impact order, or in some instances a physical match. But a lot of times the pieces are going to be a lot smaller, so we're going to be trying to work with the physical and optical properties of the glass itself. Things such as the color, the type of glass, surface features, flatness or curvature, the thickness, fluorescence, density, elemental, and also the refractive index of that sample itself. But in many instances, you are able to determine the direction of the force or the order of the impact, or in some instances that two pieces of glass were one at an earlier time by obtaining a physical match of those pieces. You might also be able to determine what type of glass it is. So is it a flat glass? Is it a molded glass where you can actually see the seams of the mold itself? Or are the chemical characteristics of the glass consistent with heat-resistant glass or specialty glass? In a lot of situations, you'll be working with the optical and physical properties of that glass, trying to determine whether or not it is actually consistent with a known sample. And we can do this by examining the glass particles for the various physical and optical properties. The color of the glass can be determined and compared. Whether it has any tint that has been added into the glass itself, if there are any surface features present, if it has any curvature to the glass itself. At times you can also measure the thickness of the glass. Depending on if that glass has some fluorescence, you might be able to compare the fluorescence of the glass particles. Remember, with your float glass production method, that liquid glass is actually floated on liquid tin. So at times small sections of the tin are imparted into the glass itself, which can cause the fluorescence under specific wavelengths of light. You can also determine the elemental and the density properties of the glass itself. The elemental composition of the glass is going to be because of the various chemicals that the glass is made up of. So depending on the formers, fluxers, stabilizers, and any additives that make up that glass product, you'll have a different elemental composition. And you can see from flat glass, which is normally soda lime glass, it has a lot of silicon oxide composition, where your headlamp glass is also going to have silicon oxide, but it's also going to have boron in the glass itself, where your soda lime glass is going to have calcium. So your elemental composition can give you good indications as to what type of glass you're also dealing with. The elemental composition of the glass itself is usually performed on a scanning electron microscope or an ICP, two of the instruments that we discussed during instrumental methods. You can also determine the density of a glass and use that as a comparison feature between known samples and any foreign samples from crime scenes. Density is going to be a physical property and it's going to remain constant, so it can be used to characterize the glass sample. It is done through two different methods, either through the density gradient tubes or through the sink float method. When we use the density gradient tubes, this is more of a comparative examination. When we use the sink float method, the analyst is able to obtain a numerical value for the density of that glass sample. They may also determine optical properties for the glass particles themselves. The refractive index is one of the most useful properties for glass identification and also for glass comparison. There are two different techniques that are used in the forensic laboratories to do refractive index determinations, and both of these take advantage of a phase contrast microscope. We discussed very briefly in the microscope lecture about a phase contrast microscope. This microscope has two different components that are placed into that optical light path of the microscope, which help create greater contrast for viewing samples. So the phase contrast microscope is used to view your sample, and in the Emmons double variation method, the wavelength of light and the temperature that the sample is viewed at also vary. When you use a Grimm 3 method, only the temperature varies. Both of these take advantage of a Becky line. This is a halo that's actually created around the interface of the particle and any mounting media. The halo will move with respect to the boundary as the microscope is focused either up or down. This occurs because the particle is either acting as a converging lens or a diverging lens. If the particle has the higher refractive index, it's going to act as a converging lens, and as you increase the focal distance, that halo or the Becky line is going to move inside the edge of the particle. Likewise, if the particle has a lower refractive index, the particle is acting as a diverging lens, and that halo is going to move outside of the particle. Glass evidence can be found at a wide variety of different types of crime scenes. So you can consider it as possible evidence in homicides, rapes, assaults, even arson and criminal mischief type cases. It is usually detected by a very good visual search that can at times be combined with different light sources or the application at different angles. So usually you can find glass particles with your naked eye with natural light, but lighting from angles might also assist. In most instances, having greater magnification can aid in detecting glass particles. So a lot of times, items may be brought back to the forensic laboratory where a stereo microscope may be able to be used to actually locate extremely small glass particles, or in some instances, even glass that is more of a powdery type sample. When we collect glass samples at a crime scene, usually either tweezers are used or the hands are used to collect your larger glass samples. Smaller glass samples can be collected through a variety of methods, either by, once again, using tweezers, in some instances, scraping down items may actually recover glass particles out of the items themselves. So if someone had on gloves and they broke out a window, some of the small glass particles may be embedded in the glove itself, where scraping that glove down may be an easier way to retrieve the particles from that fabric. In some instances, taping or vacuuming may also be used. You always need to remember to collect known samples if you're at a crime laboratory. If you're wanting to do the glass examinations to determine the side that the glass was broken from, you need to make sure that you collect the entire window itself, and then also mark from the frame a couple of the pieces, which side is actually inside and which side is outside. If you're collecting the known glass for comparison purposes, where you're going to be asking or performing optical and physical property examinations, you need to collect a good representative sample. And usually this means taking samples from the four corners of the window itself. You need to package glass so that it's going to preserve that glass for the analysis. And there's a wide variety of different products that can be used, but remember, if that glass has sharp edges to it, you have to prevent it from being able to get out of the container itself. In some instances, you might want to also protect that glass. If you are wanting to determine impact points or knowing which impact point is first, second, and third, you're going to have to package that glass so that it's secure, so that it's not going to continue to break. So if you have a windshield that you're wanting to determine impact points, it might be necessary to take that windshield out of the vehicle, but then to package it so that it's not going to continue to break as it's being transported to the laboratory. Also, for physical matches, this is very important. You don't want that glass to continue to break before the analyst has the opportunity to work on it. Once again, you always need to make sure that your containers are adequately sealed. So seal them with tape and then put your initials over that tape. Glass evidence has been used in courts for many years. Usually the reports from a physical match that a glass examiner may perform, they're either going to be able to say that the glass was one piece at an earlier time, or that it could not be physically associated with another exhibit. In most instances, there's going to be instrumental and microscopic comparisons done on the glass particles. So the examiner in these situations can usually state that the glass is either different from another exhibit, or that the glass might be identical to another exhibit in the color, type, layers, elemental compositions, the various optical and physical properties of that glass itself. In some situations, they might have to state that it is only similar to a glass if the testing cannot be complete, if they only have enough of the sample to do a partial testing. Next, we'll talk about another form of trace evidence, soil examinations.